that worked during his bachelor on learnable signal processing to detect and understand bioacousticals. And he then shifted towards deep networks from a theoretical perspective by employing affine spin operators during his PhD. He is now working at FAIR with Professor Yann Lequin on bridging the gaps between the theory of deep learning and the best practices in numerous applied areas, such as self-supervised learning, fairness, and implicit regularization. Today, he will present self-supervised learning through the view of spectral embeddings, which allow theoretical and empirical studies and offer some practical indication. So thank you, Randall, for being here, and the floor is yours.
Thanks. And thank you, Antoine, for inviting me. And by the way, I will be at NeurIPS. I think it's in 6-7 months from now. So if any of you is there and want to meet, we can get in touch over there. So yeah, basically, as Antoine said, I will try to spend first some time in this talk to motivate self-supervised learning. Because I'm not sure that everyone is really aware of what it is, and it's not really popular yet outside of pure computer vision. So we'll first go a little bit through notation from a supervised learning perspective. Then we'll move to unsupervised learning, maybe as it was done, let's say 20-ish years ago with reconstruction-based method. And then we'll move to self-supervised learning, and there I will highlight basically some recent research we've been doing here. And then we'll finish with some still open questions. And by the way, throughout the presentation, if you have any question or anything seems odd, feel free to interrupt me. It's really likely that there are some typos, so also feel free to interrupt me if something is weird. So first, in supervised setting, just to set up notation in a case that I think everyone is familiar with. So basically, we will consider the video to be a composition of many layers. And in general, we'll consider a layer to be a block of affine transformation and a nonlinearity. So it could be an activation function like a ReLU, leaky ReLU, or it could be a max pooling operation. In general, at least in the maybe previous version of deep networks, we could say, okay, you have a layer with this form, and then you can change the sort of constraint you have on the affine mapping to recover maybe a dense or linear layer like you have in MLPs, or to recover a convolutional layer if you impose like circulant constraint on your matrix W. But more recently, there's been many variants of what you can call a layer. We will not stick to it necessarily, and in fact, we don't need to be that precise after this. So it's just to set up notation and review some background. But for example, you have residual layers that emerged a few years ago, where you allow for basically linear connection between the input of the layer and the output of the layer to be an addition of the nonlinear part. And even more recently, you have a self-attention layer. So here is a simple example with a single head. So you have many different variants. We will not really go too deep into those specific details. It will not really matter to us, but yes, just to make everyone aware of those different variants. And you can no longer do simple analysis with the original layer formulation. It will not go through reviewers, basically. So regardless of this, basically the main question that we are trying to answer is, given architecture, regardless of how it was defined, we will assume for now that it's given, how to find its parameters so that we can make something useful from this mapping. So of course, how you define useful is a bit vague, but in general, it's just that you might have an application at end or a product, and at some point you can use your mapping to basically make your product better or solve some problem that was not solved before or improve performance in how you solve it. So the standard way, or maybe what is the most known way to do this, is to collect some input x1 to xn, and then try to formulate what, in your case, you think is interesting about those inputs. And so basically, this is a labeling task. So you can consider you have a labeler or an oracle, if you will. And for each object xn, it will basically tell you, okay, this is what is interesting in this, for example, image. You have a specific object in it, and you say, okay, I want the name of this object. If you have a voice recording, it could be the words that are being spoken. And of course, it's really specific to your task, right? So if you have a voice recording and I don't know, you want to do speech recognition, you'll be interested in which words are pronounced. But maybe if you are interested in predicting, I don't know, the environment where the recording is done, maybe you are interested in the background noise or other thing like this. So the type of labels that you will want for each input is entirely guided by the task you want to solve. But that's basically what you will do in supervised learning. And then once you collect those labels, you will solve your supervised learning task. So there are many ways to do it, of course, but I mean, a very general way is to try to enforce the output of your network to match the labels that you collected. And then you can have some regularizer in addition to it. And basically you update the weights, so generally with gradient-based learning, to try to minimize this loss. And so, of course, if you have enough samples and optimization is successful and you are good at picking the architecture, you will have a useful network that generalize well and that will be useful to you. So that's the main idea of supervised learning. And basically, there are some very cheap shots you can take at supervised learning, right? So I'm sure you read about those points in basically every paper that deals with supervised or unsupervised learning, but I will repeat them anyway. Basically, the first one is about cost of labeling a large amount of data. And I've just added correctly labeling because now there are many ways to label datasets that are relatively cheap. But the problem is that you have access to labelers that are not experts and you have a huge amount of noise in your labels. So I would say now it's costly to have a correctly annotated dataset. But then there are some more fundamental limitations of supervised learning. The first one is that once you have your labels and you train your network on it, in a sense, and it makes sense, right? Your network overfits to the labels or the task you trained it on. And so unless you want to use it for a subtask or a task that is relatively close to the one that you trained it on, it will, in general, poorly work. So it's really specialized models that you obtain at the end. And this basically means that once you train a deep net, you cannot use it for other tasks easily. And the training of this deep net only leverages the data that have been labeled for this specific task. And this is quite annoying because you can imagine you have different sets of data, each have been annotated for different tasks, and yet you cannot combine them all in an easy way. So of course, we have some ad hoc ways to do it, but in a general, principled way, it's not straightforward. So in a very motivating sense, supervised learning is quite wasteful. And so because of this, we moved on to unsupervised learning, where we try to basically only leverage the inputs and we don't have access to labels. So just a quick maybe motivation for those things. So in general, we will say that, of course, we don't know what are the labels to your inputs. So we don't know exactly a priori what you yourself find interesting or what you want to know about your inputs. But you can ask a slightly more general question, which is what you find interesting about the representation of your inputs. So there are many properties, and of course you can have a large amount of a priori knowledge to motivate different properties. Those are maybe three general ones. The most important one, which here I call faithfulness, if you know for better term, I will take it. But basically, the idea is that your representation is informative about your input, so you try to not forget information about your input in the representation of your input. So here it's just measure in terms of mutual information, but you can think different ways to measure this. And of course, you want this because if you have a collapsed representation, so for example, for each x, your network outputs a constant, then this is a completely useless network. You cannot do anything with it. So this is one of the most important property, and then you have other things like maybe stability to noise, maybe some parsimony or sparsity of the representation. But those come more secondary, and in general, they will require some more advanced a priori knowledge of your task. But anyway, if you have those properties, you can then come up with unsupervised learning task. And basically, again, there are many variants of it. I just put one here for illustration, but it will come down to trying to reconstruct your input using F as now an encoder and adding a decoder G. And you will try to, for example, enforce stability by adding some noise to your input and making sure that you can still reconstruct the original input, maybe some sparsity regularization on the code that your encoder produces. You can build all those families of laws basically based on the properties you want to impose. But the main idea is that unsupervised learning, at least originally, most of it was based on reconstruction. And this is how you enforce this property, basically. You cannot not have information about your input if you can reconstruct it, in short. So basically, from this, what we see is that with this version of unsupervised learning, you need an additional decoder, G. And this is not really a problem per se, because you already have an encoder with possibly millions of parameters, so it's not adding a few more that is going to be a limitation. But the main problem is that the way you design this decoder actually strongly impacts the type of representation you will learn by F. And if you want to think of the extreme way, you can see what type of representation you will learn if G is, for example, infinite width network, huge amount of capacity, versus if G is linear. You will see that the type of representations that F will try to learn are completely different. And this means that the usefulness of the learn mapping will vary a lot. So basically, you add an extra set of hyperparameters on how to design this decoder. And the other problem, which is also as important as this one, is that we don't necessarily know of a good metric to measure the reconstruction fidelity of your model, especially if you go to high-dimensional settings and maybe images or sounds. I think if anyone has done application with time series, speech, and things like this, you can see that you can measure reconstruction error with waveforms. It's quite chaotic. So from this, it introduces an extra challenge as well. And so from those points, and again, because our end goal here is to reach self-supervised learning, right? We can argue that unsupervised learning, at least reconstruction-based unsupervised learning, is also wasteful, or at least not the best way to learn a representation. So this finally leads us to self-supervised learning. So the main motivation still relies on the same sort of properties that you want your embedding or representation to have. Those are true basically regardless of the laws you try to use and so on. But the difference is how you will try to impose those properties in your encoder. So you saw that in the reconstruction-based case, basically this is just a proxy to enforce faithfulness, so to ensure that as much of the information about your input X will be present in your representation. And this was measured in terms of how good can you reconstruct X from its representation. And the point of reconstruction-free unsupervised learning or self-supervised learning in general is to basically use different proxies to enforce this property. So a very simple motivation to start with. If you have just a few samples, you can say that basically you don't collapse your representation or you keep as much information about your input as possible if you simply map each X to its own representation. And in a sense, if you think about it a bit in terms of this reconstruction law that we had before, we'll say, okay, if I have an infinite capacity decoder, then this is basically enough to have a perfect reconstruction. Each X is mapped to a different point in your space, and then you have the decoder, which is, if you want, just like a hash table, looking at what representation is it, and mapping back to the X of your finite training set. And if you do this, you can formulate a training method, which is very simple in terms of n-class classification laws, basically. So you want each input to be mapped to its own one odd vector, if you will, or just its own class, if you see this as a classification task. So again, this, you see, is a proxy. And now we don't need to have a decoder anymore. We don't need a reconstruction and a reconstruction metric. So again, you can find ways to cast this as a reconstruction method with a specific decoder and so on. But the point is to then little by little move away from this. So this already is what is known as a pretext task in self-supervised learning. And the idea is that you are given X and you define a task. Here it was a classification task, which is a pretext, if you will, to learn a good representation. So this was one of the method, I think this was around 2018 or something like this, where you're basically given inputs and you try to predict one class for each of them. And then you have some tricks to prevent basically erratic behavior during training and so on, but those are more details. It's not really relevant for us here. But then from this, people have said, okay, maybe I don't want to predict one class per image. I can come up with other sort of task that I want my network to solve. So another thing that came around was basically predicting the rotation that you apply to your input. So for example, if you have only 4 set of rotation, it will be a 4-class problem. And you are given an image and you try to predict, okay, which rotation has been applied to it. And the main motivation is to say if a network is able to solve this task, then it must have learned some structure about the image, about the object in the image, because without this, you will not be able to predict which rotation has been applied. So you need to have some understanding of the concepts present within the image. So, of course, from this, you have many variants that came around. So another very popular one is this jigsaw puzzle classification task. So basically, you extract some patches from an image, you shuffle them, and you now have a classification problem where you try to reorder those patches to say where were they originally. So again, the main idea is also to say if you know and you understand about the concept that is present in the image, you will know how to position each of those patches to reconstruct the main object. So all of those are different variants of pretext tasks, and you have a huge family of them that emerge. So you can think of it as basically having a proxy classification task, if you will. So the challenge with this is that it's not necessarily clear how to design a pretext task that will learn a representation useful enough to solve your
Ok. On va continuer à parler dans le vide. Ouais.
slide.
And so on. You actually versions of this that were used maybe in the 90s.
Randall?
Yeah. Yeah.
We lost you for a couple of minutes. Can you
Really?
go back one slide, for example?
Okay.
Thanks.
Where
Okay.
did you lose me?
Yeah.
The next one is fine.
The jigsaw one is good.
Yeah, you're saying it's hard to find good pretext.
All right,
Oh,
go
okay,
ahead.
okay. Yeah. So basically, yeah. So you did not miss much. Basically, I was mainly saying that it's not clear a priori how you define a pretext task, and the way you define a pretext task will impact greatly the performances of the learned representation. And so this becomes, let's say, a bottleneck that you need to figure out to have a useful SSL method. So from the difficulty of designing pretext task, people have moved away from this to a different way to learn embeddings, which is from a joint embedding or Siamese network approach. And then basically just to remind people, so this is slightly connected with deep metric learning and so on, and some variants or preliminary version of this have been applied quite a long time ago, but then have been mostly forgotten or let's say unused, but this is coming back since a couple of years. So that's why when you speak about joint embedding SSL, usually you refer to those recent methods that came around since 2 years ago. And then you differentiate this from deep metric learning, which are all those previous methods from the 90s and so on. But so in this setting for us, basically you introduce a small variation, which is you don't solve a specific classification task that you set up by hand anymore, but instead you are transforming or perturbing the input, and you try to enforce the representation of the same input but with two different perturbations to be close to each other in embedding space. So this is enforced with this first term here. And then you enforce this representation to be far away from all the other ones. So this is just one example of loss, what people usually refer to contrastive learning. In particular, this will be SimClear. So I did not put all the details with the temperature parameter and so on, but this conveys the main idea. And so the main task now is on sampling perturbation or data augmentation that you will apply to each of your points, and then tuning this loss correctly so that you have successful training. So now you see that you went from defining a pretext task to defining which augmentation you want your network to be invariant to, in a sense. So this is slowly going away from having a strong prior on what you want to learn. And basically, of course, you have many variants of losses and so on, but this one has been, I think, one of the first to really provide a breakthrough in performances. So just to, again, motivate a bit the strengths of those approaches, what you see here, so this is taken from their paper, you have the link here if you want to see it in text. But the main idea is that you will do training of your network only from this loss function, which does not use any labels, right? Only your augmentations that you defined a priori. And then the way you evaluate the quality of the representation in this plot is by freezing this network at the end of training, and then adding a linear classifier on top that you train on ImageNet with its labels. So you don't update the encoder, the network F, you just learn the linear probe on top of it. And what you see is that basically, just from this, you are able to nearly match the supervised setting. So of course, if you have the same amount of parameters, you have a small gap, but still you go from, let's say, 77 to 70 top one accuracy on ImageNet, which is a really strong baseline. This shows that the quality of the representation you learn is really high. And you see, so this plot is interesting because you see other methods. So for example, this big GAN is the representation of the discriminator from the GAN training. And you see that qualitatively it's much less, let's say, good or accurate than the SimClear case. So again, the motivation is to say that embedding SSL, which tries to match representation of two differently perturbed input, and then prevent collapse by enforcing that overall your representation cover all your space, is quite powerful at learning high quality representations. So now, of course, just said like this, you might say, okay, then there is not much research to do, right? But actually, this is how joint embedding SSL is solved. But in practice, it's not as simple. So first, one difficulty is that during training of your SSL loss, you don't just use your network F, but you actually use a composition of your network F and an extra network G, which is often known as a projector network. So you do training with this composition of two networks, and after your, for example, SimClear training is completed, you throw away the projector network and you only keep your loss F. So already this is the first trick that is a bit annoying because you need to set up and design this projector network carefully. And the way you do this has a strong impact on performance. So this is already something that is quite annoying. The second problem is that the current SSL methods have been built basically by having hundreds, maybe not thousands, but hundreds of people trying everything by hand and looking at the performance of their method on ImageNet and tweaking for example, SimClear parameters and so on to maximize this ImageNet performance by hand. So in a sense, you could say that current joint embedding SSL is extremely biased or favors computer vision task and natural images. And the last thing is that currently most of the ways to evaluate and compare methods, so for example, if you compare it to a supervised training network, or if you compare different SSL losses, is done from a linear probe applied on it. So this is extremely not clear why this type of evaluation is good or representative, and there might be different ones where actually you see that maybe even a reconstruction-based method could perform equally with SSL method. So there are still a few open questions. And at the end, I will discuss about a few more, but first I will describe what we did to try to answer each of those ones. So, and just, yeah, also I forgot to add this detail, but although the SimClear loss seemed relatively simple, the new versions that came around since 2 years are actually extremely involved. So if you think about this, so those are diagrams I directly took from the paper. So you can think of those diagrams are already, quite pre-processed and simplified by the authors, right, to sell their method. And yet you can see that it's quite a lot of engineering to reproduce their method or just to implement them. So what you see is that we are actually having a huge engineering overhead, if you will, of the current loss we use. In addition of this, all of this has been done on ImageNet, so it's extremely hard to just take a method and deploy it somewhere else. So just to start with something simple, let's look at the role of the projector. So there is one first visual analysis that we did now, I think more than a year ago, which is based on training a conditional diffusion model to simply basically invert the features that are learned and try to see what information about the input is preserved. So if you know things like, for example, deep image prior and all those type of methods, they try to learn inverse mapping from learned features to, for example, pixel space in this case. But the problem is that the quality of the samples is relatively low, and the way you define your decoder is biasing the visuals you get. So here we just extend this method to diffusion models, which are currently state of the art to produce high quality samples. And we use this by, and then we condition it on the representation to provide visuals of what the representation contains in terms of information. And so what you see, so each row is a different SSL method. So you have SimClear, Dino, VCraig, and Barlow twins. And then we compare the inversed feature with different sampling of the same conditioning, which is on the left column here. We compare the representation of the visuals when we look at the output of the backbone, so the output of F, versus the output of the projector, so the composition of F and J. And what you see, just from this very simple visual analysis, is that when you look at the output of F and J, actually you don't keep much information about your original input. So some methods might keep a bit more. You see SimClear, for example, you still preserve the fact that there is grass, it's a sort of small animal in the original image. But then this is not so much for other cases. But at the output of the encoder F, you see that basically you preserve almost all information about your input. So maybe you don't preserve the orientation, right, this left-right flip, but everything else is preserved. So from this alone, this visual, let's say, inspection, you can see that the performance at the output of F is actually greater because you preserve much more information about your inputs, and it's very likely that this extra information will be useful for the linear probe to solve the task, the downstream task that you consider. So from this, you see that the projector learns, in a sense, a poor quality representation. And so that's why, because of trial and error, people have come up with this trick of adding it and then removing it after training. So this already provides a general tool that can be applied everywhere. But then we went in a little bit more depth on this projector. And if you look at transfer learning or out of distribution literature, it turns out that this trick is actually quite common. So the fact that you maybe add an extra few layers during training and then you remove it, or maybe in those papers it was formulated differently, so you train with the same F, but then after training you remove the top layers, so same formulation, right? And basically this trick was found to provide better generalization because intermediate representation, of course, have more information about their inputs. They don't overfit as much on your task. And so because of this, if you have, for example, noise in your labels, or you want to transfer to other domains, throwing away the last few layers is a very cheap and useful trick. And so this is exactly what people are doing in SSL. And so what does this mean? This means that the loss that we currently use is not maybe correct or is too noisy. And so we try to identify where does this come from. And so one very interesting finding is that if instead of using two augmentation of the same image to define a positive pair, instead of this, you use the labels. Again, the goal is not to have a new SSL framework, right? It's to debug, so we allow ourselves to use the labels. We use the labels and we sample two images from the same class, and now we define those as a positive pair. Then suddenly, there isn't much of a gap anymore between projector and output of the encoder network F. And of course, there is still the role of the hyperparameter and so on that plays into account. But you can see if you pick the right hyperparameter in the top line, then you can basically keep the projector and you have as good performances. So from this plot alone, and by the way, the full link of the paper is here if you are interested. But the whole takeaway from this analysis is that if you either don't have the right data augmentation or the right definition of what you call positive pair, and you also don't have the right hyperparameter, then the representation you will learn will be extremely biased, and so it's good to have the projector to absorb this bias and to remove it post-training. But if you were in a perfect setting with good data augmentation and good hyperparameters, you will actually not need to remove this projector away. So from this, you can understand that maybe if you try to deploy your SSL model in a new modality or for a new task, and you cannot afford to cross-validate everything, it's actually a good practice to do this trick. And by the way, as a fun side joke, the title of this paper involved guillotine regularization, so you should check it out. So the second or another viewpoint on the role of the projector is by considering it to be random and not learned. So basically, if you do this small assumption, then you can go a little bit further and understand what the projector, how the projector helps to learn good representation beyond just this bias fitting, if you will. So one thing that you can do is for some specific SSL losses, so especially VCraig, Barlow twins, this family of loss, you can go, if you keep a random projector and you minimize your SSL objective, then this projector will actually enforce pairwise independence in its input, so at the output of the encoder F. So now, it's not really clear if pairwise independence is something you necessarily want, for example, for classification task and so on, but at least you can probably show that this property will be enforced as long as you don't learn your projector. And so this is really interesting because from this finding alone, you can do two things. The first thing is that you know how to change the architecture of your projector and how to tweak it so it does this in a stronger fashion. And this is what we did here in this right top. And by doing different tweaks like this, we can actually improve the performance. So here we only considered VCraig, but of those methods. And another thing you can do is to actually use this insight and move away from SSL to actually use this for more simple tasks like ICA. And so we see here is a very simple validation, but you see that basically VCreg, so here it's only VCreg, we don't have the invariance term, but can be used to solve ICA, again using this trick. So from this understanding, we see that the projector might still have some benefit, even if you have the good loss, if you want to impose some specific properties like pairwise independence. And you also obtain different intuition. So for example, if you do ICA and you resample the random weights of your projector, you can actually have a very small, so it's computationally effective, very small projector and still get a really good ICA performance. So again, all of this comes simply from trying to study the role of the projector in SSL. So we get a bit more understanding into the role of the projector. But there is still another question now, which is, okay, this is interesting, but what about picking different losses? Because you really have a huge amount of variance that exists now. For example, just if you consider SimClear, you have a prototypical version of SimClear, you have SimClear with a different denominator, you have SimClear with a different metric. So a huge amount of family of losses exist. So the second question that we ask is actually, do we really need that many variants? And can we find settings where maybe they either fall back to the same thing, or at least we understand when it's to be preferred from another? And so this is something that we answered in this paper, where basically we try to connect joint embedding SSL methods with spectral embedding methods. So basically, just for a quick background, spectral embedding method was, I would say it's still popular, but maybe was more popular a few maybe 10 years, 10, 20 years ago. And it includes things like Laplacian game maps and so on. It's a way to provide a nice manifold learning or a dimensionality reduction method of a dataset. And usually those are non-parametric methods. So it relates to a lot of things, PCA, kernel PCA, special cases, and so on. And the main interest is that the literature in spectral embedding is extremely rich, and it is more or less known when one variant is to be preferred from another, depending on the properties of your data, the dimensionality of the intrinsic manifold, and so on and so forth. So the goal here was really mostly about reformulating current SSL methods under this viewpoint. And this involves basically the definition of a relation or a graph between your data. And this is quite insightful, so I put here, and by the way, again, you have the link of the paper here if you're interested. Basically, if you consider supervised learning, right, then you can see each image as a node in your graph, and all the images of the same class are connected to each other. And so if you have only two classes, for example, you have this type of graph that comes up. And if you look at standard self-supervised learning with only positive pairs, then you have only nodes that are connected with each other 2 by 2. And so from this, you can simply use this and try to see, okay, from this graph formulation of the relation we use in SSL, how can we then cast the specific losses in terms of spectral embedding losses? And it turns out, surprisingly, that you can do this exactly for quite a lot of methods. So, for example, you can see how vcreg basically recover Laplacian game maps, how simclear recover multidimensional scaling of the kernel version of it. And then from this, you can see, for example, if I have a linear network and my graph has this property, actually doing any of those methods will learn the same representation. So I don't really have to cross-validate which loss do I use in practice. I can just use any, it will produce the same representation. And from this alone, you can see that the cross-validation space, in a sense, that you have to go through is much reduced, especially if you know properties about either your network F or your graph G. So from this, basically, this was a first study, but we hope that from this, there will be a lot of results, maybe on generalization guarantees and on deriving new improved methods. Because again, spectral embedding is a really rich literature and background, so SSL for sure can benefit from it. And then another thing that we did was to say, okay, SSL and joint embedding SSL is nice, but right now it's mostly applied with large deep networks on computer vision and so on. But in practice, you might have scenarios where you have only small data set, for example, or not necessarily image data set, and you cannot have the luxury to train a deep network. Or maybe in general, you could say, okay, you don't have access to a GPU, for example, or something like this. Although I think it's pretty rare. I've heard even in France now there is this huge cluster recently that has been deployed. But anyway, there is still some settings where maybe you don't want to use a deep network. So one thing that we did, it was to basically find a kernel inspired by SSL. And the main idea is that you only have, so it's a bit similar to also semi-supervised setting. The main idea is that you have known positive pairs for a huge amount of data, and then only known labels for a few of them. Then you can come up with this kernel formulation, which enables you to basically learn a nice embedding of your data and solve a classification task. And this is quite interesting because you don't have to train a deep network, so suddenly a huge amount of hyperparameters go away, and it can provide quite interesting insights. So for example, I put here two classification settings, MNIST and EMNIST. And the number of training sample is given in the title. So you see the classification performance is really low for MNIST, but it's because we use very small training size. And basically, the first row is when we use Gaussian blur as augmentation for the positive pairs. So in a sense, for MNIST, you can say, okay, this might have a very small interest, but it's not really the type of transformation that is naturally present in MNIST. And the second row use rotation, translation, and zoom, which is much more aligned with the type of natural transformation you have in MNIST and in EMNIST. And what you see, those three lines, is two supervised benchmarks. So the first one, the blue one, is when you only use the data and labels from the original training set without any augmentation. And so in a sense, you can say it's the lower bound, or what you could do if you did not know any augmentation or anything else. And the black line is when you have the labels both on the original data and on all the augmentation that came out of it. And then in red is the performance you get from this, I will say roughly SSL kernel, where again, you only use the labels of the original data and then the non-pairwise relationship between the original data and all the augmentations. And what you see is that, of course, if you don't use the correct data augmentation, you don't perform good, and you might even perform worse than if you were doing classification with the small amount of labels. But if you have the good data augmentation, you actually match very closely, and you can even outperform the fully supervised setting, let's say. And this is really interesting because you can get this type of performance really quickly because again there is no training, and this could be a first step maybe in finding which data augmentation will be useful for your SSL method if you wanted to just use this as a way to select which data augmentation to use to train your deep network. Or of course you could use this as a standalone if you want as well. And so this is also on archive if you want to check it out. But we were really surprised by the fact that you can actually find settings where you outperform the fully supervised case. So this can open interesting avenues even in pure kernel field, let's say. And the last thing we did, pre-last thing actually, that we did is to solve one of the more fundamental problem in SSL. So right now, people pick their hyperparameters and architecture by using the SSL loss, but monitoring the supervised performance on ImageNet with a linear probe with disconnected gradients and so on. So it does not interfere with the SSL learning, but still you have a sort of oracle that guides you during training. And this is really unrealistic, right? Because the whole point of SSL is to provide an unsupervised method. And yet, if you wanted to now use the SSL method on a new data set, there is nothing that can tell you, okay, your training was successful or not. Everyone will tell you, well, just use your labels to know what's happening. So it defeats the whole point. So what we did is very simple and you might say naive construction of a statistic, which is simply based basically on the rank of the learned representation. And from this, you can rank the quality of different representations that was learned. So this does not use any label, it's just looking at the rank of the learned representation. And surprisingly, although very simple, this is a quite good indicator of how your embedding will perform. And the logic here, although simple, is quite intuitive. So the main idea is that if you use a linear probing, basically, if you have a small rank versus high rank representation, you will have different training set performances. And because you only use the linear probing and in general the downstream task have a lot of sample, you can roughly assume that you will not overfit too much. And so just looking at this simple metric is actually quite correlated and indicative of your test set downstream task performance. And so we validate this on a few data set and models. And what you see in this table is that if you do hyperparameter search using what we call this ImageNet Oracle, so using the labels, versus using hyperparameter search using this RankMe method, you actually end up learning a set of hyperparameters which is not too far from optimal, but at least now you do so without using any labels. So again, the goal is to try to move away from using any label at any point, whether it's in the deployment or in the development of your SSL method. So I think this is also one of the really interesting research area in SSL. It's starting to pick up now, but there are for sure a lot of things to do. And then the last thing that we looked at is, okay, so now we know to train roughly SSL on ImageNet, right? But in a sense, ImageNet, although it's large, you have a lot of classes and so on, it's still really nice. In a sense, you have class balance mostly, and you don't have a lot of noise, or at least the amount of noise maybe is roughly the same among classes. But if you were to learn a SSL method on completely uncurated data, it's possible that the underlying cluster or classes are not uniformly distributed. Maybe you have a lot of noise for some and not for the others. And this is quite a problem. And why? Because basically we show theoretically that all current SSL losses have an implicit uniform prior on the clusters that are learned in the latent space. And this is really akin to k-means. So if you think of k-means, right, you also have this implicit uniform prior. And if one cluster does not have as many samples as another, you obtain, as you can see on the right, you obtain a clustering that is really noisy. And so this is quite problematic because if you want to use the representation to solve some task, you don't want this quality to really vary if you change the class balancedness, right? Because again, you are in a unsupervised setting, and so you want to be robust to this. And so we obtain a slight variation of current SSL method losses, and we show basically here with a really simple experiment, all this little change, basically in short, instead of assuming uniform prior, now we assume power law prior, or in fact, if you know the type of prior that you have, you can do a simple prior matching, basically. And then from this, you can really improve the quality of the representation that you learn. So here is a really interesting example. So we created artificial data on CIFAR, you see on the left, where basically we stick the MNIST digit in part of the image, and the rest of the image is a grayscale CIFAR image. And so what we do is that the MNIST digit have lower law distribution. For example, we have a lot of 8, then much less 9, then much less 5, and so on. But the CIFAR have a uniform prior, you have class balancedness. And so what we show is that if you use our method with a prior that matches the MNIST one, so a power law prior, and you do your SSL training, and after training you take an image, a reference image, and you look at the training set images that are the closest in embedding site. Then you actually pick up the class of the MNIST digit. So you add the prior that matches the MNIST prior, and so basically you learn a representation that puts close together images with the same MNIST digit. And conversely, if we use the uniform prior, so the standard SSL one, then once you look at the nearest neighbor of those images, it's no longer about the MNIST class, but it's about the CIFAR class. And so what you see from this is that you have some very subtle things you need to really take into account when you deploy your SSL model. And it will be, in this case, for example, about the prior of the class or cluster that you try to encode. So this is something that we did, and you can quantify this precisely and motivate this. But this, let's say, bias or uniform prior appears regardless if you do Craig, Sinclair, Barlow twins, or more recent variants. So basically, those are the main direction, let's say, that we look at. And so just to conclude briefly, there are a few open, actually I say a few, but a few main branches, but a lot of sub problems that are still open in self-supervised learning. So I think one of the main issue right now is in terms of training speed. So basically, if you are given a specific amount of epochs and you compare how the training curve and the downstream task performance evolve in supervised versus SSL setting, you will see that SSL learns at a much slower rate than supervised training. And so far, not much progress has been done on that front. And this problem seems to be valid across the SSL method. Another problem is basically how do we define your right augmentation? So it's really akin when we looked at the pretext task, which pretext task you define, this impacts the quality of your representation. Here we went a step back, but still there is a huge impact on the choice of data augmentation you use, especially for the positive pair. So there is some result that I did not show here, but basically we find out that for the negative pairs, the augmentation does not really matter, but the positive one is really important. And there are many cases where someone does not know which augmentation to use. So this is also a huge limitation of SSL today. And then the last one is that the current methods are quite unstable to train and unstable to hyperparameter change. So what I mean by that is if you're in a supervised setting and you maybe don't pick the right weight decay or I don't know, the right architecture and so on, yes, you will have a drop in performance, but you will not go from state-of-the-art to random. But if you are in SSL, this can very easily happen. You can change by a small factor, one hyperparameter, and suddenly you are basically with random performances. And so this sensitivity is extremely problematic because it means when you do cross-validation, you need to spend a huge amount of compute on this. So those are some very interesting questions, but there are of course many more, and yeah, we are happy to collaborate. If you are already working on this or you want to chat, feel free to ping me as well. So yeah, that's it on my end. Thanks.
Thank you. Okay, so do we have questions here? Do you have any idea why this is so sensitive to the changes in those parameters?
Yes, so that's a good question. So the current way to think about SSL is that you have, so for example, let me look at this loss here. So you have this type of loss, right, with a positive pair and then negative sample that prevents the collapse of your loss. But basically, if your network, for example, is extremely over-parameterized, the way you can find a configuration of your points to solve this loss can vary. And just changing the weight decay, for example, or maybe the training time will impact this a lot. Because if you don't move too much from initialization and you have a strong prior in how you define your architecture, right, then you cannot really move too much from this maybe nice regularized thing that you had at random initialization. And so you have a high quality representation. But if you move too much away, you can basically have an arbitrarily random representation. And this is not the case in supervised training, right? Regardless of your model, when you solve your training loss, then at least you know that for those training points, you predict the correct class. And then if you are lucky to have a large enough data set, then maybe that's all you need, right? So just the fact that you don't have this extra constraint makes those questions suddenly much more important. And so that's one of the problem. Basically, you don't really have this sort of equilibrium point, which is at least good enough for the training points when you do SSL training. And so you become really sensitive to those extra parameters. This is, by the way, this sensitivity is much less if you look at pretext task like this. So this might also be something useful to explore. Basically, maybe there is a way to combine the two as well. But yeah, relying only on matching augmented samples is a very really tricky configuration to get to still a good generalization.
Okay, other questions here?
You said one of the main problems is to find the right augmentation, but we also find that the correct augmentation depends on the data, whereas the goal of self-supervised learning is to be able to generalize. So it's even possible to find like a data augmentation that is kind of generalizable, or do we have like representation that will be good for like a certain amount of task and another for other tasks?
Yeah.
Or
Yeah, that's a very good point. So basically, by picking your data augmentation, you bias your representation. And so a priori, it means you will favor some downstream task over the other. So saying that you find a universal data augmentation maybe means that you will sacrifice performances, especially with linear probing on some task, but at least you will be better across tasks. And that's one of the things that people were doing, right, when they were doing denoising autoencoders. Basically, in a sense, they were saying, okay, my augmentation is just white noise. And that's one of the things that we try to do now with SSL, to make them work where the augmentation is only some white noise perturbation, because in a sense, it's the least, if you will, biased augmentation. And so you will learn a representation that does not try to overfit a specific downstream task. But the problem with this, and it comes out to how you evaluate your model, is that very naturally, if you do linear probing on ImageNet, your performance will have a huge drop. And so what this means, probably, and I'm sure there is a very simple way to show it, is that if you want to be competitive with supervised learning only with a linear probe, you probably cannot get away from knowing the exact data augmentation that you need or the exact invariance that you need for this specific downstream task. So you cannot have a universal, let's say, SSL model that will perform equally good across tasks just with a linear probing. But that's maybe also artifact of using linear probing, right? So that's why there are many questions like this that are still open. And maybe you can show, okay, with linear probing, then you cannot have a single general augmentation to be good across different downstream tasks. And this is exactly this type of result that will be useful, because at least it will remove maybe some cross-validation or something that people are trying, and it will be a guide to say, okay, instead of doing this, maybe train, I don't know, 3 different SSL methods, each with different data augmentation, and then you combine them together or something. Because yeah, right now, we don't have a lot of guidelines in SSL. But yeah, that's exactly the type of question that might be easy to answer and could be really useful.
You said that learning SSL is slower?
So it's slower to train. So if you take a specific network, let's say a ResNet 50, and you compare how basically the performance are and how they evolve throughout the epochs compared to a supervised method, then basically you see that the supervised case reach already, for example, 90% of the best you can already after 10 epochs, let's say. But SSL has a much more, let's say, linear growth in the performances. And you need to train for basically 10 times more epochs to reach this plateau effect where it does not really improve the quality of its representation. So this is one problem right now. And it's a really strong problem because it's not just that you have to train longer, it also means that if you want to do cross-validation, you need to train 1,000 epochs instead of 100, let's say, to be able to tell if your model is good or not. Because after 10 epochs, you still did not pick up any useful signal that is informative of the final performance. While in supervised setting, already after 10 epochs, you can see you are already at like 90% of the, maybe not 90%, but really almost all of the best thing you will get after longer training.
But on the other hand, maybe it's the price to be paid for learning a model which is good for everything.
So that could be true, but at the same time, from deep metric learning background, there are actually a lot of papers showing that, when you do this positive pair versus negative pair, or you pick the negative pair really matters and can impact training convergence. So my guess right now would be that it's more about we don't have the right loss or maybe the right way to apply it. Maybe you should not apply it on random mini batches, right? And maybe we cannot match supervised trainings. It's for sure, right? And I think that's your point. But I still think there is a huge margin between where we are now and supervised training, and I'm sure we can do much better than what we have now. And probably there is some tricks to pick from deep metric learning and those things to do so, because that's a problem that you also had in this area.
But on the other hand, you didn't illustrate the fact that your model is good for everything, because you always compare to ImageNet classification accuracy. So
yeah.
How can you defend this? How can you pretend that you have a model which is good for many different tasks, even if it's only done on ImageNet?
Yeah. So actually, I don't know if I put any table here, but so usually people compare not just on ImageNet, but on So here you have like some examples. So you have like iNaturalist, Sun. So there are still natural image classification tasks. And usually, actually, that's one of the benefits of SSL, is that, and that's why SSL is becoming popular, is that if you were to use just ImageNet and train a supervised model, and then extract this model and see how it performs on another data set and on another task, it will give you some performance. But now if you do SSL training on ImageNet, then you extract the model and you try to do this other downstream task, it will perform better and often much better. So the goal is to, in a sense, have a method that maybe does not solve everything, but at least solve more than the supervised counterpart that you will have. And for sure, the fact that you design strongly the data notation means that, of course, you will not be good on all the tasks. And in fact, as we said a bit before, right, if you wanted to be good on all the tasks, you will have to basically learn the identity function, right? Because as soon as you lose any tiny bit of information about X, then you can by hand construct a task where you will be arbitrarily bad. So that's why when I say like all the tasks, maybe it's most of the interesting tasks in computer vision. But regarding the training speed and convergence, so basically, if you look at how the representation evolve and how much change there is between training steps, the convergence rate, if you will, is extremely slow, and it's not clear that this is related to the fact that you want a more general representation or whatsoever. It seems to be really more related to gradient dynamics of your losses and having a lot of noise in the augmentation you use. Most of the time, for example, you might not sample informative augmentation for your positive pairs or things like this. So in a sense, it's as if you have labeled noise, and this impacts convergence a lot. So that's why I think there is a lot of things to pick up on that as well.
Yes, so this is a similar, very similar remark as the Tony. Is that, I mean, since we train it with augmentations, which can be very noisy, and I don't know if you also use some type of corruptions, because now a very big topic in machine learning is also robust machine learning. So maybe these models, if the type of noise applied, I don't know, for example, maybe some fog or some snow or this kind of thing, maybe you are also naturally more robust. And do you, I guess you also compare not just on clean ImageNet, let's say, but on corrupted ImageNet, and is there like better performance?
Yeah. So there are a lot of studies looking at performance on. So I think so far they mostly look at things like adversarial examples and so on, and they found you are slightly improved robustness. In terms of robustness, people also look at distribution shift, right, and OD generalization, and it also seems to work better. But there isn't really a principled way, let's say, to measure this because now. Everyone compares on ImageNet trained model with a specific data augmentation pipeline. So you cannot say, for example, SSL is more robust. It's more SSL with this specific pipeline tuned this and with this architecture. Then this might be more robust than the supervised case that was trained with a different pipeline and so on. So as far as I saw, you don't really have an apple-to-apple comparison yet to really say that. And in fact, for sure, you can find specific augmentation pipeline where your robustness will be extremely bad. Because again, this comes back to this problem of saying if you have a slightly wrong augmentation pipeline, very quickly your performance can drop and can be basically close to random. Because you can you can minimize the SSL loss without learning anything meaningful about your data, basically. And that's one of the main problem of SSL right now. It's all to, at the same time, get away from this reliance on data augmentation, but not sacrifice any performance that we had. So it could be, so we have a lot of people working on using less biased, let's say, or less informed data augmentation. So for example, instead of saying, okay, you have translation, grayscale, color jittering, solarization, flip, blah, blah, blah. You only have one, and it's, for example, random erasing. So you put some block in the image to zero. So at least it's a bit less informed and less biased, right? So that's one big push. And maybe then once this will be developed a bit more, there will be a way to measure more principally, okay, with this pipeline, are you still more robust or not to this distribution shift or this noise than supervised training? But again, so far there is no really apple-to-apple comparison, simply because the supervised model use one data augmentation pipeline. Those guys use another one. I mean, everything is different, right? So it's a bit tricky to say yes or no.
I understand. Thank you.
I didn't understand why you call this method rank me. Where's the rank?
What did you say? Where?
On this slide, why do you call this rank me?
So it's basically pun because rank me is because we rank the quality of the different SSL representation. And it's also related to the rank of the embedding because we look at the entropy of the distribution of the singular values, which is if you want a smooth version of the rank of your matrix Z. So that's why it's called rank me. So it's if you want, it's a smooth version of how you will compute the rank of a matrix, which is just looking at the entropy of the distribution of the singular values of your matrix.
Okay,
Those sigma are the singular values. Yeah. Sorry, I not put enough background on this, but yeah, basically, you extract your singular values, you renormalize, and you compute the entropy. And we in the paper basically we also compare with the maybe more strict definition of rank by counting the singular values above a specific threshold, and the same trend emerge. So it's this specific definition is not really crucial. The main point is to monitor the let's say spectral collapse of your representation. Again, it's really intuitive, but it turns out it's quite predictive of ranking the quality of SSL methods, learned representation.
Okay. Are we done with questions? Thank you very much, Randall, for this extremely clear talk. Very informative. A lot of things to think about.
Thanks. And by the way, if you have any questions, you can either send me an email or ask Antoine, and he will forward it.
Okay.
To answer
Okay.
it.
So thank you again. So you're going to start your day in New York City now? Where are you?
Yeah, I am in New York City now.
Okay. Okay. Beautiful. Thank you.
Have a nice day.
Have a nice day then. Bye-bye.
Thanks, you too. Bye-bye.
Il y a quoi, il est 6h? Ouais, 6h, 8h peut-être. Là, il est 9h là.
Il est 9h chez lui?
Il m'avait proposé encore plus tôt.
Bon alors, je sais pas si ça a été enregistré du coup. Hein.
Ah bah, on va bien.